a lot already on the other day. So, okay, so why don't we start this off? Math 350. Review. This is sort of review number 2. And I'm going to just continue doing more practice problems primarily, because I think that's what everybody needs, probably what everybody wants for the most part. So let's jump in. I'm going to do a lot of stuff on chapter 3 this time, but let me start off maybe with something else first. So let's do this, and I'm going to call this number 6 because I believe on Monday I did 5 practice problems, so I'll be able to just add this to the handout and then send it back out to everybody with the update. Okay, so let's start off with the first example, number 6 here. Let's try to prove the following statement. If A is countable. So in the first review, I gave you some specific sets and asked you whether they were countable or not. In this one, what I'm going to do is give a little more theoretical result. This is actually part of a proposition that I ended up not ever getting around to proving. If A is countable and A twiddles B, then B is countable. Okay, so this is what we are going to prove, and I'll just as a reference for this, you might take a look. This is actually part of proposition 2.11. So I did state this result in the class, but we never proved it. And Nazgal, you're the only one out there in the Zoom, so feel free to unmute yourself if you have any questions as you're going along. We only have a couple of people here as well, so it's perfectly okay.
Okay, thank you.
Of course, of course. Okay. So for a problem like this, there might be a part A where I first ask you to define what a countable set is. So make sure you know that definition. It's a very important one. Does anybody remember what it is? You can make a bijection with the natural numbers, or it's too finite. Exactly. So the set is either finite or it has a bijection with the natural numbers, which is what this twiddle symbol means. So it's an or definition, which means that you probably will need to do cases to prove it, right? So for this proof, let's go ahead and see if we can write it down. We're assuming that A is countable. So since A is countable, we're going to do 2 cases, right? So case 1 will be that A is finite. And case 2 will be that A is in bijection with the natural numbers, right? That's basically what countable means. It means that either A is finite or it twiddles the natural numbers. Okay? So let's take them one by one. We essentially have to prove both cases. If we start with a finite set, and if it twiddles another set B, can we say anything about that? Do we know any results on that? Objective. All right, so since A is finite and A twiddles B, do we know anything based on that about B? Then B is finite. Yeah, then B is finite. That is by proposition 2.8. And again, you don't need to know the proposition numbers for the exam. You can just say that this was a proposition from the book. I would accept that. Or it was done in class. If you wrote that down, I would be fine with that as well. But B is finite, and hence, as we know, a finite set is also countable. So hence, countable, and so we're done in that case. So in that case, B is countable, and we're done. So far, so good? So remember, finite implies countable, but not the other way around. A countable set might be finite, but it also might not be. It might be in bijection with n. Okay, let's look at case 2. Let's suppose that there's a bijection from A to n, and we also have a bijection from A to B. So we're going to maybe try to put that together. So since A twiddles n and A twiddles B, then you're thinking of transitive. Transitive. Yeah, this twiddle is transitive. So if one thing twiddles another thing, and then the second thing twiddles the third thing, then actually the first one twiddles the third thing. You actually proved that in your homework, that if you compose two bijections together, you still have another bijection. So I can do that, and I'm even going to use the not just the transitive property, but also the symmetry, the symmetric property to say that, look, if A twiddles B, then B twiddles A. And we already know that A twiddles n, so therefore B twiddles n. This would be by properties of twiddle, which again, we did state those properties in the lecture. Okay, so you could just say from class or something like that. Anything that we did in class, guys, you are welcome to use. Anything that is in the book, you're also welcome to use, even if you don't remember the number of it or what exactly it is. Just don't use something that we've never talked about. Don't use something from chapter 9 of the book, for example. We haven't gotten there. It should be something that's in the realm of the material that we've already covered. It should be in that mindset. So yeah, so once again, so B is countable. So in both cases, then B is countable. Okay, great. Let's do let's call this 6A. And then I'm going to do a part B because it's related to it. Part B is just going to say if we have f, which is a function from A to B, and f is 1 to 1, and A is uncountable, prove that B is uncountable. Excuse me. Okay, so this is continuing along the same topic here. Let's see if we can write down a proof for this. If we have a one-to-one function and the domain is uncountable, I want to prove that the codomain is also uncountable. I'm wondering if anybody has any thoughts about how to do that.
Since it's injective, that means f of A is its own thing, which is a subset of B. So f of A is a subset of B, which is uncountable.
Now, f of A is always a subset of B, but the important thing is what you're starting to spit out there at the beginning, which is that because it's injective, right, the A and the f of A are basically the same. They are in bijection with each other. So even though f might not be onto B, it is onto whatever its range is, right? It's onto whatever it's onto, to say it that way. So we know that A is going to twiddle f of A since, this is just another way of writing the image of the function, right? F of capital A. This is just since f is 1 to 1. Okay. Thus, by what I'll call the contrapositive of part A, so the contrapositive of part A would say that if B is uncountable and A twiddles B, then A is uncountable. So I'm gonna use that here. A is uncountable and it twiddles something else, so that means f of A is uncountable. So it's the big size of infinity, uncountable. Is that so far so good?
Mhm.
Okay, so f of A is uncountable, but then since f of A is always a subset of the codomain, which is B, so here you got a subset relationship. The smaller guy is already uncountable. So then, so is the bigger guy. B is uncountable. This is actually also by, I'll just say C proposition 2.11 again. Proposition 2.11 says that a superset of an uncountable set is still uncountable. Okay. So again, you don't need to know these numbers so much, but when we're taking notes during the review session, these are just little hints to remind you to maybe go back and look at those again. Okay, so yeah, so that's a kind of a nice follow-up result as well. Are so good? Okay, great. Let me come back over here. Everything good out there?
Yes, thank you.
Okay, great. And I am recording, so it's coming out okay. Perfect. Let's do another problem. Let's just do this one. I kind of like this. So I said I'm going to do quite a bit of stuff on sequences today. Let's go to number 7 here. Let's prove that if xn is a sequence in Z, so it's a sequence of integers, then xn converges if and only if xn is eventually constant. So for the integers, if we have sequences of integers, it's very easy to talk about when they converge. They converge exactly if and only if the terms are all eventually constant numbers. What this just means, I'll just add a little bit here to give it a little more mathematical notation. This just means that there exists some natural number, I'll call it n naught. So n naught exists in the natural numbers such that if n is greater than or equal to n naught, then xn is equal to xn naught. This is what eventually constant means. It means that there's eventually a subscript to your sequence, such that all of the later subscripts are just the same as that one. So after, if n naught is 100, it would mean that for all of the terms starting with x100 and beyond, they would all be equal to each other. Okay, so this is what we would like to prove. Okay, this is an if and only if statement, so I am required to prove it in both directions. It's really a two-part proof. Let's just start with maybe the forward direction here first. And so that means I'm going to assume that the sequence converges. Let's just say that it converges to x. Okay, so obviously x would end up having to be an integer, but we don't need to start off too strongly with that. Let's just say x is some real number, but we could prove that x has to be an integer as well in this case. So I'd like to prove that xn is eventually constant, right? So let's remember the definition of this. Xn converging to x means that for all epsilon greater than 0, there exists and not such that, and then on from there. And we're assuming that this is true, which means maybe we should choose a specific epsilon. So this is usually the way this works. If you have the assumption of convergence, the way you're usually going to take advantage of that is, at least if you're using the definition, is you're going to take advantage of that by specifying a value of epsilon. Epsilon smaller than 1, we can try to make our neighborhood so that it only has one integer in it, right? Yeah, maybe we can always go back later and edit our epsilon. We can always go back later and edit our epsilon. Sorry, I think my internet was a little shaky there for a second. Based on that epsilon, then by definition, there exists an n naught. Now, we shouldn't just automatically assume that this n naught that I'm bringing up right now is going to be the n naught that we need to find up here. Okay, but let's just see how it works out, right? We can always go back and edit this a little bit. So there exists this n naught such that if n is greater than or equal to n naught, then the absolute value of xn minus x is less than 1/2. Okay. And I'm trying to show that all of these xn's are actually the same as each other at this point, right? We good so far? So these are integers. Let me just draw a little picture here. Here's x, and I'm making a neighborhood around it of radius 1/2. So this is x minus 1/2. This is x plus 1/2, right? So that neighborhood can only contain one integer because the width of that whole interval is only 1 unit. So there can only be one integer in that in this region, and the xn is in that interval as long as n is greater than or equal to n naught. It's in there, and it has to be an integer. So it has to be the same integer over and over again, right? That's basically the idea here. So how do I actually want to say that? I think, yeah, the point is I haven't said that x is an integer. If I had said that x was an integer, then these are two integers. So if their difference is less than 1/2, it has to be 0. That's really what we want. So is there any way that the xn could converge to a non-integer? No. So maybe I'm going to put a little asterisk here, and I'm going to come down here and make this claim that x actually has to be an integer. Let's just do it this way. Okay, I'm going to make this sort of side claim first, and then we'll be good to go. Why does x have to be an integer? Let's suppose, by way of contradiction, that x is not in C. So let's assume x is not an element of Z. And what I'm going to do is let's let m, which is an element of Z, be the integer closest to x. So if x is not an integer, then, there'll be some m, maybe here's m plus 1, and maybe x is like that. So the x, the integer that's closest to x, we could call that m. And then if we set epsilon to be the absolute value of x minus m, okay, so that would be strictly positive since x and m are obviously not the same. Then the neighborhood that goes from x minus epsilon to x plus epsilon, that neighborhood contains no integers. Right, because what you're doing is you're making a neighborhood around x that has a radius that's right out to the edge of where m is. So this is x minus m, and this is x plus m. Sorry, that's x minus epsilon and x plus epsilon right there, right? So you're making a neighborhood of that radius. This contains no integers. And that contradicts the sequence being able to converge to x. Because xn, the sequence then cannot converge to x because it cannot get within that neighborhood. That make sense? So if I assume that x is not an integer, it's pretty obvious. I'm just trying to figure out how to write it. So if x is not an integer, all of these xn's, they have to be on the integer line because xn is a sequence in Z. So then all I have to do is make a small neighborhood here that reaches out so that its radius is too small to have any integers in it. Then this neighborhood doesn't have any, let's just say it this way. This neighborhood doesn't have any of the terms of the sequence in it. So forget about finding an n naught such that all of the terms beyond n naught are within the neighborhood. None of the terms would be within that neighborhood, right? This neighborhood, x minus epsilon to x plus epsilon, right? It has no xn in it. So xn is not going to converge to a point that's inside of there. It's not going to converge there. So that's a contradiction. And so x is an integer. Once I know that x is an integer, I'm in great shape because these are two integers being subtracted. So this is an integer. And if its absolute value is less than 1/2, then it has to be 0. So since xn and x are both in Z, we conclude that xn is equal to x, and this is going to be for all n greater than or equal to n naught. So it's exactly what our definition requires. So that's the proof of the forward direction. Okay. Let me try and convince you that it works the other way too. So let's assume for the backward direction that xn is eventually constant. Okay, so there exists an n naught in the natural numbers such that if n is greater than or equal to n naught, then xn is equal to xn naught. Yeah, so that would be the starting point. And I would like to show that xn converges. What do we think xn converges to? prove convergence, it's always nice if you know what it's gonna converge to. So keep in mind, after a certain first few terms, after a certain point, all of the xn's are just equal to this number right here.
So X and O.
That's gonna be it, right? It's gonna be it. It's gonna converge to x and naught. Absolutely. That's a reasonable claim to make that it would converge to that particular value. Okay, so I need to prove it, and now I'm proving convergence of the sequence rather than assuming it. So that flips everything around. Now, instead of picking an epsilon that's specific, here I have to go super arbitrary with it. And I have been telling people to just write a rubber stamp on this let epsilon greater than 0 be given thing. And I see a lot of people not doing that. I see people writing for all epsilon greater than 0, blah, blah, blah. Let's just fix it here. So fix this epsilon, write it exactly like this. When in doubt, copy my notes verbatim. Don't go off on your own thing unless you're absolutely sure it's going to be right. So this is going to be perfectly good way to start. And my job is to find an n naught such that if n is greater than or equal to n naught, the absolute value of xn minus xn naught is less than epsilon. So where are we going to find our n naught from?
N greater than N naught.
We already have an n naught, right? This n naught was already here. That's actually the best candidate I can think of for the n naught that we need right now. Okay, so we've already got an n naught. Normally, this is the point where we now go fishing for an n naught. It's like, oh, well, we have to go do our scratch work. We have to work backwards and solve for n naught. Well, here we don't have to because we already have an n naught. Now, just because I'm calling this n naught doesn't mean that it's the n naught that we ultimately need to use. But it is a number that we have in our hands that is coming from the definition of eventually constant that we could at least try. We could at least try that. So we are going to use the n naught from above. And then once we've done that, so we didn't really have to go on a fishing expedition for this one. The n naught is already there. So all I have to do now is say, okay, well, let's let n be greater than or equal to n naught. And what I want to verify is that if I take the absolute value of xn minus whatever the limit is that we're claiming, we're claiming xn naught is the limit. And we need this to be less than epsilon. Well, what is it?
0.
It's just 0, right? Right, we're assuming that that's just 0, so of course that's less than epsilon, and so of course I'm done. Guys, eventually constant is a really strong assumption, right? If you're telling me that your sequence is eventually constant, there's not going to be a whole lot of struggle to figure out what's going on with your sequence. It's got to eventually be fixed at that value. So yeah, so that's a proof for that little problem as well. Okay. Everybody all right with that? It's number 7. All right, let's go ahead and try another one here. I'm going to stick with this theme of working on sequences here because I think that we could use a little bit more on that. So let's do number 8 right here. And this is going to have a few parts. The question is just going to be, does xn converge? Or in other words, does the limit exist? There were a couple of these on the homework the other day where it just asked you, yeah, does it converge or does the limit exist? And I had a few people just write down yes or no on the homework and just no justification, just no, yes or no. So obviously I'm going to want justification for whatever the answer is on something like this if it's a yes no question. But let's take this one first of all. Let's take xn to be equal to n cubed divided by n squared plus 2n minus 7. The first thing you're going to want to do is try to think about whether you know what the answer should be first. Because whether it converges or not dramatically impacts your process of either justifying that it converges or that it doesn't converge. So you kind of want, even without writing a whole lot down, you just want to get an intuition behind it for yourself so that you can be confident that you have the answer right. And then we can figure out how we're going to prove the answer. But the first thing is to just figure out what we think the answer is. So I've got all three of you. Anybody have a thought that intuitively, do you think that that will converge or that it will not converge? Yes? No? Now, so you're the tiebreaker.
I think it will converge. It's going to be 1 over, so it will converge.
It's going to be 1 over, what do you mean?
So like if you divide all of them by n to the power of 3, it should be 1 over like something, so it's going to converge.
Let me try that. I'm going to try your idea. I'm going to divide everything by n cubed. Is that what you're going to say? So if I divide everything by n cubed, then on top I'd be left with 1. On the bottom, when I divide everything through by n cubed, I'll have 1 over n plus, oh, I'm sorry. Yeah, that's right.
Yep.
Plus 2 over n squared, and then minus 7 over n cubed. Hmm?
Oh no, I was just talking to myself.
Okay, so then we can ask ourselves, where does this, we have our limit theorems, right? The limit theorems would say, all right, this is a fraction, so figure out the limit of the numerator, figure out the limit of the denominator, and then form that quotient. But there was a little asterisk on the quotient one, which is that this only works, that process I just described only works as long as the limit in the denominator is not 0. Well, if you look at the denominator, you have 3 parts here. Each of them is converging to 0. So it doesn't work. Okay. So guys, we should have the intuition here this should just be straight, clear. N cubed grows much faster than n squared. I'm just talking about the intuition behind it. Right? So we're not going to be able to prove that this converges. This is going to be a no. It's not going to converge.
Does that apply to kind of like what we were doing on Monday? Just how to take in the midterm? Where you say if your numerator is bigger than your denominator, it's most
Yeah, just looking at the powers of n on the top and on the bottom, the highest power of n. If the numerator has a higher power of n, then the numerator is going to grow faster than the denominator. And so as a fraction, the whole fraction is going to tend towards some flavor of infinity, either plus infinity or minus infinity. And that would mean that it's not converging, essentially. Okay. So anyhow, yeah, so the intuition here is that no, this should not converge. How would we prove it?
We're gonna divide through by n over 2 and set that equal to that, and then we'll use our rules of limit.
Divide through by n squared. So a moment ago, we tried to divide through by n cubed. That didn't really work. If we try to divide through by n squared, we'll get something like this.
You do the sum of the limits.
Okay, so I can definitely get, this time I'll certainly get the denominator converging to 1. But what about the numerator? Goes to infinity, right? So again, our limit theorems, as much as we love to use the limit theorems here, the problem is that, again, we're not allowed to have infinity as sort of one of our pieces of our limit theorems. Those limit theorems work great as long as you have specific fixed numbers for each thing. So I agree the limit of the denominator is equal to 1 right now, but on top I have something that, I mean, intuitively, sure, you could say, well, that's infinity divided by 1, which should be infinity, and that diverges, right? But that's the hand-wavy explanation that I don't really recommend here. I want to go with something that's going to be a little more rigorous. I'm going to give you maybe 2 ways to do it, to justify this. One way would be to just do it by way of contradiction. Now, suppose that so let's actually start writing that down. What you can do here is you can say, by way of contradiction, let's assume that xn does converge to some x, right? So we could certainly do that. And we actually we actually can do what we just talked about a moment ago. We can divide this through by n squared everywhere. So that, the algebra of that is totally fine. So just taking the sequence and dividing it through by n squared would be totally fine. But then what you have is you have n times, I'm going to write it as 1 over 1 plus 2 over n minus 7 over n squared, right? So actually, what I'm going to do, sorry, give me a little bit more room here. What I'm going to do is I'm going to take, I'm going to do it this way. I'm going to go ahead and put the n back there again. I'm going to multiply this by 1 plus 2 over n minus 7 over n squared. Now, that's equal to n. The denominator is just canceling that. This is converging to x by our assumption, and this converges to 1 by the limit theorems. And if they are both converging, so if this converges to x and this converges to 1, then the limit theorems says that their product converges to the product of the limits. So this would then converge to x times 1, which is x. See what I mean? So you would be proving that then what you've basically proven is thus n converges to x. This would actually prove that n converges to x in this case. And what's the contradiction with that? Do we have a result we could use? What kind of a sequence is this? It's increasing. It's monotone. I'm looking for a different word. Starts with a B.
Bounded.
It's bounded. It's unbounded, actually. Starts with a U. It's unbounded, right? What do we know about, do we have any results about convergent sequences versus being bounded? I think it's Prop 3.2. It says that convergent sequences have to be bounded. We proved that a couple of classes ago. Convergent sequences have to be bounded. Well, here's a convergent sequence. So by proposition 3.2, the sequence n is bounded. And that is clearly a contradiction. That is definitely not bounded. There is no b such that n is always less than or equal to b. So yeah, a convergent sequence, if it converged, it would have to be bounded. Okay. Now, my second solution is basically the same thing, except that just applying it directly to xn. If xn converges, then this thing is bounded. And you can kind of think about this again intuitively. As n gets large, this thing blows up. So solution number 2 is that if xn converges, so this is also by way of contradiction, it's just being done a little bit more directly from the original sequence, then xn is bounded. So convergent sequences must be bounded. That's really what I wanted to review out of this. However, n cubed divided by n squared plus 2n minus 7, that is not bounded. If you just said that, I would probably just take that. It's kind of clear that the numerator is going to explode faster than the denominator. I wonder if we could make it a little more rigorous. So let me just look at this for a second with you guys. I would like to convince myself that this is not bounded. Maybe I can play a little game here where I make the denominator smaller. So, you know, this, if I make the denominator, I'm sorry, I want to make the denominator here bigger. Because then this fraction would be smaller than this fraction. I can make this denominator bigger if I just simply don't subtract 7 from it. That would certainly do it. And I could make it even bigger by, again, making the denominator, I can make the denominator even bigger by replacing 2n with something that would be larger than 2n, I don't know, maybe 2n squared. That would be even larger on the bottom. And this is just n cubed over 3n squared, which is n over 3. So if you want to convince yourself that this is not bounded, you can compare it to something smaller that is also not bounded. This thing here for sure goes to infinity. And so therefore this one would go to infinity. So you could do it that way as well, kind of comparing those sequences. That actually reminds me. Yeah, okay, so maybe I should. Well, first of all, I want to make sure, is everybody okay with this example? So far, so good. So either one of those proofs would work. By the way, so there was one in the homework that you just turned in, homework number 7. Let me just find this problem. I didn't choose to grade it, but it asks you, again, basically, does this converge? I guess we could call this part B for problem number 8B now. What about -1 to the n times n all over n plus 2? So you guys did this one for homework. It should look familiar. I think you did it for homework.
That's right.
This is problem 1B from section 3.2. Did I assign that?
Yeah, A, B, and C.
A, B, and C for this. Yeah, so I'm pretty sure this was a homework problem. So how could we have done this one? You can kind of tell that the n over n plus 2 is kind of converging to 1, but then it's oscillating with a plus minus, which means it's really not going to converge, right? So one way you could prove that, so this is also, this diverges, and the proof, I don't know how you guys did this problem, but I would do it by way of contradiction. I would say, assume that -1 to the n times n all over n plus 2 converges to x. So just assume it does converge. And then I'm basically going to do the same thing, the same trick that I used over here on that previous example. I want to isolate the part of the sequence that doesn't converge. This one we know does not converge. How can I compare that one to what I was given in the first place? Well, it's obviously what I take what was given and I multiply it by basically the flipped over version of n over n plus 2. So that's just the algebra that you can use. Okay, so I want to go real slow with this for a minute because this is a powerful strategy that I didn't really do an example directly in class. When something diverges, what you can do is you can assume it does converge. And then you can extract the part of it that's really going to make it diverge, which is this. This is really the problem. We know this diverges, but we can sort of split that off by using a reciprocal here. So this is just literally algebra. N over n plus 2 cancels the n plus 2 over n, leaving me with -1 to the n. But the point here is I now have two things that both converge. The first one converges to x by the contradiction assumption, and the second one by the limit theorems converges to 1. Okay, So what you've proven now is that -1 to the n converges to x, and that is your contradiction. So this is the way I like to do it. Notice I'm not having to use an epsilon and not argument. I'm literally just saying, by way of contradiction, suppose it does converge, and then use the limit theorem. So this is where the limit theorem is being used, right here. Limit theorem, that would be a theorem 3.2. And in this case, we're using part B, which is the one about multiplication. But that's a nice way to do it. Okay, I like that. It's clean, it's succinct. You don't have to get your hands messy with this epsilon thing. So it's the same thing I did right here, basically. I did the same thing over here. I said, okay, you know, let's take this thing, assume it converges, right? But then split it into two parts that include the part that converges, but where it's equal to something that clearly doesn't converge. So it's kind of a neat idea.
And then versus your excellent.
Yeah, if your xn diverges, that's what you would use. If your thing converges, then, you know, then you could just use the limit theorems directly to do that. But that kind of leads me to the next part here. Are we okay? That's A, B. Everybody okay out there? By everybody, I mean you, Nasco. Okay.
So, well, like, for example, that right there, you could do, then n3 equals 1 over n plus 2, blah, 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 finds the inverse of that. Which would say that, okay, this obviously converges times something that we know doesn't converge. Okay.
Right, exactly.
Okay.
Yeah, that's a nice trick, isn't it? Yeah, I didn't really explicitly do this in class, but it works really well here. Okay, let's do another one. I kind of like that. It just avoids having to do the epsilon analysis.
Got an option up here in 3.6 then.
There you go. All right, let's try part C. Let's let xn equal, give yourself a little room to write this one down, 2n minus 3 all over 3n plus 5, quantity cubed plus 1, all over 2n minus 3 over 3n plus 5 squared minus the quantity 2n minus 3 over 3n plus 5. That's your sequence. A little fun with this one. Actually, this one isn't that bad. I tried to make it look bad, but it's actually not too bad at all. Again, the first thing you want to do after you get it written down, which takes a while, is get your intuition juices flowing about whether you think it's going to converge or whether you think it's going to diverge. Anybody have any thoughts on that? Nasco, you can jump in too if you have an idea.
Replace that with x. And notice that x is gonna be less than 1 whenever n is greater than 2.
Mhm.
And you get up with x cubed plus 1 over.
Well, what about just looking at this? This is what you're talking about replacing with x.
Mhm.
Well, what happens to that thing as n gets big?
It goes to 0.
Does?
Right.
N goes to infinity? So if n goes to infinity,
Oh, yeah, it goes to 2/3.
goes to 2/3. Yeah, it goes to 2/3, right? So we could notice here, so for the solution, I don't even know what the answer is yet, but I just want to look at that piece. 2n minus 3 over 3n plus 5. This is where you can do the whole thing where you divide through by n. Right, so 2 minus 3 over n all over 3 plus 5 over n. And we can just say, okay, well, that converges to 2 minus 0 over 3 plus 0, which is 2/3. So that little piece of it is converging to 2/3. So that means that this converges. And therefore, so does this, and so does this, and all of these are finite numbers. So what can I do? We don't have any problems with getting 0 on the bottom or anything like that, right? So we're in pretty good shape. We can just go right into the answer. I made it look like a really hard expression, but by the limit theorems, I can just say, look, the numerator converges to 2/3 cubed plus 1, and the denominator converges to 2/3 squared minus 2/3. And you can check that, you're not dividing by 0, obviously. And this is just the fact that limits respect subtraction, addition, and multiplication and division. They're all in there. The 4 fundamental arithmetic operations: addition, subtraction, multiplication, and division. And I guess I worked that out at some point and got 35/18. You can check me on that. If this was on the exam and you left it like this, I'd be okay with that. Because I don't really care about the crunching the numbers without a calculator. You just leave it unsimplified. That's okay. Does that make sense?
Yes.
That's all you have to do there. If I gave you this one, I would be thinking of it as like a nice warm-up for the exam. It looks bad when you first glance at it, but then it actually turns out not to be bad at all. Okay, I'm gonna do one more, unless there's any questions on this one or comments. Okay, if not, let's do one more. Part D, let's take xn to be the nth root of 1/2. So the square root of 1/2, the cubed root of 1/2, the 4th root of 1/2, the 5th root of 1/2, yada, yada, yada. I want to know, does that sequence converge? And then we're going to justify the answer. Grab a paper from my office. Let you think about that for just a second. So far, do we have any idea about whether we think it converges? What do you think?
Converges to 1.
Converges to 1. Okay, let's see. What do you think?
Same.
Same thing. Converges to 1. Converges to 1. Okay, that's going to be the claim. Okay, so the claim here is that this one converges to 1. Now, we don't have any limit theorems about roots. And so this one is not going to be quite so, straightforward with the limit theorems. We're actually going to need to maybe think about doing this one a little bit more brute force, bare bones. What do you want to do?
Can we squeeze it?
Squeeze it? Let's see. So it's definitely going to be, this will be definitely less than or equal to 1. Actually, so what you could do at this point, you could use the fact that this is monotone and it's increasing. So it converges to its suit, which is going to be 1. So we could actually kind of use that idea from yesterday. But yeah, I don't know what you'd squeeze it between. You'd have to squeeze it between something else that converges to 1. Obviously, 1 itself converges to 1. Okay, so if I could do that, like if I could, obviously this is true. If I could put something here, and if this is just a constant converging to 1. If we could find something here that converged to 1, we certainly could use the squeeze there. But the problem is I'm not sure what to put here that would be clear to use. I mean, I could put like the nth root of 1/3, which would be smaller than this. But the problem is nth root of 1/3, I don't know that converges to 1 any more than I know that this one converges to 1. So I would have just the same kind of challenge. But good thing to bring it up because the squeeze theorem is something we've talked about. It's a tool that we do have. So
What about ln?
the ln of what?
We play with those. No, I'm just saying that the thing itself, the
Uh-huh.
ln of x,
Oh, you want to take the ln of this thing. So let me write this in a slightly different form. This would be the 1/nth power of 1/2. So we could look at the ln of xn, and that would be equal to the ln of, I'm going to tell you right now, by the way, that this is not going to work.
no, okay,
But I like your thought, and I just want to explain kind of what's wrong with it.
Okay.
And so we could think about taking the ln of both sides and then using the property of ln, which is that the 1/n comes down.
Mhm.
So you get a 1/n in front of the ln of 1/2. And this is obviously a constant, but here we have an n. This is, if so, we would know that this whole thing converges to 0.
Mm.
That would be fine, because this is, again, the limit theorems. This 1/n goes to 0. ln of 1/2 is just a constant. And so by the limit theorems, this does converge to 0. The issue then is, how do you go from ln of xn back to xn? And you can exponentiate both sides. But that requires you to know that the ln function is continuous. So we have to know something we haven't quite gotten to yet. That will be in the next chapter. If we knew that this was a continuous function, then we could certainly exponentiate both sides and get xn converging to 1. But let's, I like the thought. It's definitely a nice idea, but we have a little bit of a lack of knowledge about continuity at this point to be able to do that. Basically, one of the hallmarks of a continuous function is that if you have a sequence of points that converges, then if you apply the continuous function, it converges to the image of the limit. This implication is true for continuous functions, but it's not true for random functions that might not be. So that's the only thing. So we can't use that. I don't see how to squeeze it. We don't have any limit theorems for it. So what's our last ditch effort? When all else fails, what are we gonna have to suffer through? There's something we can always do.
so there's some calculus property to
Nothing weird. No, this is something we do all the time.
start shoving it in,
Start shoving it into what?
start shoving numbers in the end and see what happens.
Well, that kind of helps us figure out what the claim is here, but it's not gonna do the proof.
Oh, assume we don't.
We could do by way of contradiction. But that isn't the first thing I'm thinking of. I'm just thinking of doing the epsilon and not definition. Just do it from definition. Let's just try and do it from definition, right? So the definition would say, all right, let's let epsilon greater than 0 be given. And now our job is to find an n naught, so we're going to come over on our scratch over here. Everybody's doing a good job on writing out their scratch work and doing it kind of off to the side. I really like what I'm seeing from that. So the scratch work would be, you take the absolute value of xn, which is the nth root of 1/2, minus what you claim the limit is. And you set that to be less than epsilon. Okay. And our job is going to be to try to find an n naught out of this whole thing. Okay. So let me unwrap these absolute value bars. So remember that if you have the absolute value of something less than epsilon, that means that between negative epsilon and epsilon is where your expression lies. So the nth root of 1/2 minus 1 would be between plus or minus epsilon here. I'm trying to solve for n, basically. I'm trying to solve this for n. Now let's add 1 to everything. So 1 minus epsilon is less than the nth root of 1/2, which is less than 1 plus epsilon. Okay. And I'm trying to solve for n. Right now, the n is upstairs as an exponent, because this is, let me go back to the way we had this before. We're gonna come back around to what you suggested earlier. So we have that, I want to solve for n. Logarithm, right? They'll take the logarithm of both sides, so this goes if and only if. I should have if and only if arrows here on all of these. So I can take the ln of 1 minus epsilon less than 1 over n times the ln of 1/2 less than the ln of 1 plus epsilon. Now, I do have to be a little careful here. Again, this is not something I would take off for, but I do have to be a little careful because if epsilon was more than 1, then you would be talking here about the ln of a negative number. And that doesn't make sense, right? So that would be an issue. However, it turns out I don't really need this side of it. It's really this part over here that is going to give me my n naught, because I want to solve this for n, which is currently in the denominator. To get it into the numerator, I have to flip it over, and that will allow it to be a n greater than something. This one is definitely positive. I mean, this is definitely more than 1, so this totally makes sense. So I am going to take reciprocals on this. So I'm going to get n over the ln of 1/2. Okay, I just flipped that over, greater than 1 over the ln of 1 plus epsilon. So you just flip that guy over like that. You know what? Can I try this again? I actually want to take this 1/2 and write it as a 2 to the negative 1, and then pull the negative 1 out. So I'm going to pull that negative 1 out. Negative 1 over n ln of 2 less than ln of 1 plus epsilon. Let's do that. Just want to be careful with this thing. Now I'm going to just multiply through by n. I'm trying to get n by itself in the best way that I know how. I'm going to multiply through by n here. And then I'm going to divide by, so you just always have to be careful if you're multiplying or dividing on both sides, whether it's a positive or a negative expression. Multiplying through by n is no problem. It doesn't change the direction of the sign. And dividing by the ln of 1 plus epsilon also doesn't change the sign, because that is also positive. So this becomes negative ln of 2 over ln of 1 plus epsilon. Huh. This is very interesting. This is actually n greater than a negative number. It just doesn't make sense. Something is wrong here. I didn't write down enough of my notes. I have this problem somewhere. I can look up the details on it. But the point is that I shouldn't be able to just let n equal 1 here. So this is a negative, n greater than some negative number. But if n is 1, I just have a half right here. And epsilon might not be bigger than a half. It could be smaller than a half. So something is wrong.
What if you didn't take the negative out
Um,
when you turned your ln of 1/2?
oh, this one?
Yeah, what if you left it 1 over 2?
It shouldn't matter. Shouldn't matter. Oops. It shouldn't matter
That would be
because
1 over 2.
I'd have to take out that minus, but this is a 1 over 2.
Yep.
And then I multiply through by n. All right,
Yep.
I can do that. All right, that's fine.
Now we're legal.
Everything's legal. The problem is this is still a negative number, because the ln of 1/2 is negative,
Oh.
and the ln of 1 plus epsilon is positive. So I actually think we need to keep this. You know what? So if epsilon is bigger than 1, which would make this invalid. If epsilon was bigger than 1, you know what? This would automatically be true already from the very beginning, because nth root of 1/2 is somewhere between 1/2 and 1. So how far away is it from 1? Well, not very far. It's less than 1/2 away from 1. So if this epsilon was more than 1, we're already done. Right? So, you know, if epsilon is more than 1, then for all n in the natural numbers, the absolute value of the nth root of 1/2 minus 1 will be less than epsilon, and we've already got it. We're already good to go. So then what I can do is I can say, let's assume now that epsilon is actually, in fact, we can even make that for epsilon equal to 1. So if epsilon is 1 or more, we can do that. So let's now assume that epsilon is strictly between 0 and 1. And if that's the case, then I am actually a-okay with working with this ln of 1 minus epsilon. So let me come back in here and put it back in. If I multiply through by n, I'll have n times ln of 1 minus epsilon here. And so I get a condition here, n is greater than ln of 1/2 divided by ln of 1 over epsilon. And over here, so if epsilon is between 0 and 1, this is going to be a negative number. 1 minus epsilon will be, well, sorry, 1 minus epsilon will be between 0 and 1. Just this part in here. If epsilon is between 0 and 1, then 1 minus epsilon will also be between 0 and 1, which means this is a negative number. So when I divide by it to isolate the n, I'll have to turn this around. So this n will become greater than ln of 1/2 over ln of 1 over, of 1 minus epsilon. And guys, this is a negative over a negative, which is a positive, which is a good thing. That is actually what I wanted. This is kind of worthless, as it turns out. It doesn't tell me.
Killed the wrong side.
I did played with the wrong side, exactly. So anyway, so assuming that value for epsilon, then what we can do is by the Archimedean principle, there exists an n naught in the natural numbers with n naught greater than ln of 1/2 over ln of 1 minus epsilon. So there you go. That we can do. And so if n is greater than or equal to n naught, then n will be greater than ln of 1/2 divided by ln of 1 minus epsilon. And now we can retrace the scratch work. So retracing the scratch, we get absolute value of the nth root of 1/2 minus 1 less than epsilon, which is what I needed to do. Okay, so that fumbled me up for a minute, but we figured it out. That was 8A, B, C, and D so far, right? Okay.
If you left the other side, it just says it's also greater than a negative number.
This one?
Yeah.
Yeah,
They
this
flip the
is
sides of the
this is not wrong. It's
Yeah.
just not helping me.
Yeah.
It's not helping me at
Yeah.
all. So we can just
It's positive.
yeah, exactly. Exactly. Yeah. Okay. All right, I'm happier with that. That looks very reminiscent of the solution that I had. Okay, I think I'm going to do one more problem and then call it a day. And this is number 9, right? I'm gonna need somebody to give me it was problem 6, 7, 8, A, B, C, D, and 9 so far. So I think this is the last one I'm gonna do, and this is actually from the group work number 3, problem 3. Nobody had time to actually do this during class the other day, so I thought, well, let me just do it with you guys. So there's a definition here that I'm gonna put down. What does it mean for a sequence xn to converge to infinity? This means for all alpha greater than 0, there exists an n naught in the natural numbers such that if n is greater than or equal to n naught, then xn is greater than alpha. Okay. So that's given as a definition. And again, you can look this up in the group work number 3 if you need to. I'm gonna ask you a couple of little things here to try to prove. So part A is just going to ask you what should it mean what should it mean to say xn converges to minus infinity? So this is just kind of asking you to take the definition that's already up there and tweak it around to work for minus infinity. So I am gonna let you guys try to tell me what you think is next. So first of all, let's just make sure we understand this definition. You know, our sequence, I'm going to draw kind of vertically here. There's some alpha. If you pick any alpha, then there exists an n naught so that eventually the terms are above alpha. They're north of alpha at some point. Yeah, so thoughts about what the definition should be? Can we translate the statement a little bit? Want to try it, John? Okay.
All beta less than 0,
Less than 0. Okay.
there exists an n naught as
Uh-huh.
an element of n,
Right.
such that if n is greater than or equal to n naught, then xn is less than beta.
X(n) is less than beta. Yeah, that's how I would do it. Right? Nastikal? Yep. Exactly. So you just turn the inequality around here, right? So instead of xn being required to eventually be north of alpha, then instead there's a beta here that's less than 0, and the terms of the sequence should eventually be less than beta. Absolutely right. Okay, I like that. So that's that would be the definition. And now I want to do a part B, which is that I would like to use that definition to prove something. Let us show that xn equals 6 radical n minus n converges to minus infinity. 6 square root of n minus n converges to minus infinity. See if we can do that. I'm gonna go see if I can find a better marker. Starting to run out of juice and markers here. Okay. So what's my rubber stamp first sentence here? Not, I don't see an epsilon on the board.
Okay,
Let beta, say it again,
be greater than, oh, less than. zero.
less than 0, be given. Okay, rubber stamp, right? Just write that down without even thinking about it. So that's what we want to do. Then what we normally do over here is we go over to our scratch, right? Go to our scratch side. And we write down our sequence, let's see, 6 radical n minus n. And we want it to be less than beta. That's kind of working backwards from this is the conclusion we want. And our job now is going to be to try to use this scratch section to come up with an n naught. We're going to try to come up with an n naught. Anybody have any suggestions on the algebra here? Oh, let me not do if and only if, because maybe we don't need to do if and only. See?
Add in the other side and then square.
All right, let's maybe make it look nicer. Let's put the n on the other side. 6 radical n less than beta plus n. All right, I can live with that. And
Square both sides?
let's get rid of that radical. Square both sides. So that's 36n less than the quantity beta plus n, which is a quantity squared. And I might need to have a little more room to keep this scratch going a little bit further. So what is that? That's 36n less than, let's see, it's beta squared plus 2n beta plus n squared. Okay. And let's see. Try to make this, clean this up a little bit. Well, how about we put the two n's together? So I'm gonna put them together over here on the left side. So 36 minus 2 beta times n less than beta squared plus n squared. So just take that 2n beta and move it over to the other side. And now what I'm going to do is something that only works backwards. But this is going to make our life a lot easier, which is I'm going to just drop this beta squared. So beta squared would be positive. So just ask yourself, if this one is true, will this one be true?
Yeah.
Definitely, because all you're doing going backwards here is you're throwing another beta squared on the right side, which only makes the right side bigger. So if the inequality was already true to begin with, adding beta squared to the right-hand side is a safe thing to do. But that would not work in reverse. Good news is I don't need it to work in reverse, right? I'm only going to be using this scratch. I only need to use this scratch work in the direction of the arrows as I've drawn them here. Now I'm going to cancel the n. Cancel an n from both sides. That one actually can go both directions again. And look what you have. You have a wonderful value that your n naught could be greater than. Notice that beta was negative, so 36 minus 2 beta is going to be more than 36. And this is going to give us an n that works. So let's come back to the proof now. Let's let, by the Archimedean principle. By the Archimedean principle, there exists an n naught in the natural numbers with n naught greater than whatever we want to write down. I'm going to write down 36 minus beta, but minus 2 beta. And so then if n is greater than or equal to n naught, then n will itself be greater than 36 minus 2 beta. And now we retrace the scratch work in reverse to get to the answer. Now retrace scratch to get 6 radical n minus n less than beta. So that's how I would do that. It's not the only way to do it, I don't think. But certainly it's a reasonable way. Another thing we could have done, guys, right here, this step, we could have. Maybe not. Maybe actually it was nice to have beta squared here so that I knew it was positive. I could drop it from the right-hand side on that backward scratch work. So yeah, I like the squaring both sides.
Beta was negative before that.
Yeah, beta would have been negative. So does this look okay?
So for this one,
Uh-huh.
since we were working with the negative infinity, we didn't have to add it under scratch. Because when we normally do it, we'll have like the absolute value of whatever.
Yeah, that doesn't appear in this blue definition. There's no mention of the minus infinity here.
Oh, okay.
So
But if
in some ways, this is actually easier than
than
having a finite value where you have to take an absolute value of xn minus x. Yeah. So in that sense, I like this even better.
So when working with infinity, we wouldn't have to worry about that part.
Exactly. Plus infinity or minus infinity, you don't have to deal with. There's absolutely no absolute values here on this proof at all. Yeah. That make a little bit of sense?
I understand the if and only if arrows. Now, the one where you just did to the left, that
This one.
means,
So can I go from here to here?
no, you can't.
Can't?
Can you?
Well, all I did to go, what's the difference between this line and this line? This line has a little extra beta squared on the right side.
Yeah.
That only makes this right-hand side bigger. So if the right-hand side was already bigger than the left-hand side on this step, then it'll be even more so true here.
Okay.
We're good. It goes backwards, but it doesn't go, in other words, this one implies this one. This one, however, would not have implied this one. But that's okay. I don't wanna go down the scratch work. I wanna go retrace back up through the scratch.
Okay.
So if this one is true, this one implies this one.
Okay. Gotcha.
You got it? Okay. Yeah. But it is important to know that what you added on the right side is positive. So that's why I like the idea that you had of squaring both sides, because that brought this beta squared into it. I was thinking for a minute, well, could I, like here, I just dropped the beta squared. Could I have down here just said, well, I'm going to drop the beta? The answer is no, I can't, because the beta was negative. Somewhere beta was negative. So dropping it here, it would not have been backwards scratch work that we could have worked through. I have to actually have it become a positive thing first. So yeah, this is actually very nice. Of course, you guys know that this has to be rigorously done. I have a lot of people in this class right now who are just waving their hands a lot. So they're saying things like, oh, well, this is infinity minus infinity, right? Yeah, we don't know what that means, right? So we don't want to just have loosey-goosey write-ups of this stuff. So try to be really precise as much as you can. We okay with that? Let's prove one last thing today. Call this part C. Let's suppose that xn is always greater than 0. So that would be for all natural numbers n. I would like to prove if xn converges to 0, then 1 over xn converges to infinity. Did you find what you needed there?
I messed up my notes in class
Oh,
probably like 2 days ago, so now I'm trying to like line
they're
them
in the
all up.
wrong order or something.
Yeah.
Oh, I see. I hate it when that happens. Okay, let's see if we can do this one real quick, guys, then I'm gonna get out of here a little bit early. when you see something like this, you always want to focus on what is it you're trying to prove. Okay, we do have an assumption, we're going to use it, but before we do that, I have to say, well, how do I set up the proof that 1 over xn converges to infinity? That means I need to go back to my definition of converging to infinity and say, what does it mean? It means for all alpha greater than 0. Stop right there. That means my first sentence is going to be,
Oh no, that.
Let alpha greater than 0 be given.
thank you, rubber stamp, let alpha greater than 0 be given. I like it. Okay, so for all alpha greater than 0, now we have to come up with an n naught. Now, I don't know what it is yet, so that's where I bring in the sort of the scratch part of my board here. I hope this is enough room. We'll find out in a minute. I'm going to use the scratch part of my board here to try to solve for the n naught. And what we're really doing with this definition is we want our sequence to be greater than alpha. Now, in this case, our sequence is 1 over xn. So we want 1 over xn to be greater than alpha. And our job is to cook up the n naught from this. So you can probably guess what I'm going to do first here.
Xn is less than 1 over alpha.
Flip it over. Exactly. I'm going to take a reciprocal xn less than 1 over alpha. This is, incidentally, this is where we're using the assumption that the xn's are positive. If the xn's were negative, then flipping things over, we have issues with the direction of the inequality. But this is positive here, and this is positive here. So flipping everything over behaves just like you would expect. You just turn that inequality around. So xn less than 1 over alpha. Now, that is going to be true because xn is converging to 0. Right? This 1 over alpha is kind of playing the role of the epsilon in the epsilon definition of convergence. See, this is our assumption. What does this assumption tell us? This assumption tells us for all epsilon greater than 0, including this one, there exists an n naught such that blah, 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 right? That's what we know. So let's take advantage of that now. I'm going to come back to the main proof. Since xn converges to 0, we can find an n naught right now in the natural numbers such that if n is greater than or equal to n naught, absolute value of xn minus 0, I don't need to write down minus 0, absolute value of xn and is less than whatever I want to put there. And what do I want to put there? 1 over alpha. And a question for you. Do I need the absolute value bars around xn?
Greater than 0.
Greater than 0. Greater than 0. So I don't really need that. So I'll just put here, this implies that xn is less than 1 over alpha. And oh my goodness, look at that. We have reached the bottom of our scratch work with our proof. So we can now just flip this over, right? Thus, if n is greater than or equal to n naught, 1 over xn is less than alpha. Which is exactly what we needed to prove, is it not? No, it's not. Oh, I made a mistake. Which is that this needed to be flipped over. Sorry. Forgot to flip it over.
Said it right.
I said it right and wrote it wrong. Got 50% credit. Okay, so that's how that one would work out. Does that look okay? I'm going to give you guys a little homework assignment, which is to try to prove that the converse of this is also true. If you start with the assumption that 1 over xn converges to infinity, then you can prove that xn converges to 0. If you get stuck on that homework assignment, you can look at the answer in the Canvas thing because I posted the solution in it's group work number 3. But it's basically just reversing most of what's going on here. So What you see on this board right now, guys, is a lot of very careful technical work. There's not a lot of hand waving here. I mean, it's okay to get the intuition, like, especially if the question is, does it converge or not? Sure, stop and think about it just by whatever sort of number sense approach you want to use or whatever, that's fine. But when it comes to writing up the final proof, try to really do it to the letter using the definitions, the epsilons, the alphas, whatever they are, they should be in there. When you're trying to use those definitions. Make sure you're not cheating with the limit theorems. If you're going to use that as an alternative, those can be used as long as every individual piece of everything you're using already converges. Okay, so it's a common mistake. I'll see people say things like n over n converges by the limit theorems. And I'll be like, no, it doesn't. This thing doesn't even converge at all. And this thing doesn't even converge at all. So I can't use the limit theorems to prove that this converges. Instead, I just need to like replace it with a constant and then say that constant sequences converge. That would be fine, right? But so just be a little careful with that. But yeah, I think this is pretty good. I would expect on the exam, I have not written it yet, but I could expect I'm going to have a question. There's probably going to be something where you have to use the definition. I might not tell you that. I might not say, oh, you must use the definition, but I might try to write a problem that you cannot really do it with the limit theorems, like the nth root of 1/2 that we did a few minutes ago. So I'll try to force you to use the definition because I feel that using that definition precisely is something everybody needs to demonstrate. But then I probably will also have a problem where, yeah, maybe you can use some of these other tools. Some of the stuff about limit theorems and convergent sequences are bounded and all that kind of good stuff. Just a thought. So I'm done a little early. How do you guys feel about that? I'm kind of on low energy mode this morning. Not too bad.
I think Monday kind of made me feel better about things.
Good. Yeah. And I am going to be back at 4 to do the review again, but I'm planning to do mostly these same questions. I can't think if there's anything else I might want to do. I'll have to look, but chances are won't be a whole lot. And in any case, I'll send out a video. And if there's anything I did add, I will add those questions onto the sheet. So you'll know that there was a change. Nazgul, how are you doing? Are you feeling okay?
Yes, thank you.
Was this helpful?
Yes, very, very helpful. Yeah.
Oh, good. Okay. Well, I'm glad that you were able to come. I'm gonna probably sign off on the Zoom session unless you have any question.
Okay, thank you. No, I don't have any questions. Thank you so much.
Good for now?
Yeah.
Okay. I have office hours later today as well. So after 8 o'clock tonight, I'm gonna do the review at 4 and then I have office hours at 8. So feel free to stop back if you think of anything later on, okay?
Thank you so much.
Take care.
Bye.